Pardon,
You are live.
Okay, so good afternoon, everyone. Our today's speaker is Raphael Oliveira, who is working at our observatory. And Raphael holds his PhD from Sao Paulo, right? Where was working on stellar clusters. And that's also the topic of his today's talk. So the floor is yours.
Thank you very much. So, hello everyone. It's my pleasure to present for you my research. So as Milena said, this is my PhD research mostly. And I expect to have the chance to present about microlensing soon for you. So the title is more or less general because I researched star clusters both in the Milky Way and the Magellanic Clouds, but with the same objectives, let's say. So these are 4 globular clusters in the Fornax dwarf galaxy. And it's interesting to look at them because they are more or less at the same distance, but have different morphologies. But so you can have a very different globular clusters. And as usual, we start explaining the classifications, globular clusters and open clusters. But hopefully there are some new information that you don't know here. So the star clusters share roughly the same age, chemical composition, distance, and reddening. And for these 4 parameters, it's not quite true. For the age and chemical composition, we can have multiple populations. So this is an exception. For distances, we can have some tidal tails or something else that's where the cluster stars can have different distances slightly. And for the reddening, we can have differential reddening depending on the region the cluster is located. So globular clusters have up to millions of stars, a very small mass range, at least for so at least for the Milky Way, they are older than 10 billion years, and they have the dimensions of a few parsecs. And in general, there's no interstellar gas, no star formation at all. And open clusters that have much less stars, they are looser, have a looser distribution, they are less dense in the center, and so on, and are obviously younger. So this is an image from James Webb. There's an offset from the center because they couldn't fill in one image such brightness of the center of this cluster. So this is let's say the outskirts of the cluster. Yeah. And dynamically, globular clusters are considered as a gravitating gas with stars being the molecules. So it's a collisional system with 2 body interactions, but it can get very complex. And so open clusters are more used to map the disk of the galaxy, so the spiral arms and so on. And since globular clusters are much older, we usually call them as fossil relics or chemical clocks, since they record the conditions of the galaxy in the moment of their formation. So some more general information here. It's estimated that 70 to 90% of stars are born in star clusters, but less than 10% of these clusters survive. And we usually we can think that it's a static bunch of stars, but they are actually in a random movement and in dynamical equilibrium, and have a lot of processes going on, such as mass aggregation, which includes the black holes in the center, and evaporation, tidal disruption, so on. And to study the evolution of the stars in clusters, we usually use the Hertzsprung-Russell diagrams, or color magnitude diagrams. And we are getting nowadays increasingly deeper and more precise photometric data. So as the telescopes are getting more powerful. About the dynamic process, dynamical processes. So we can get the distribution profiles of these clusters. Also, spectroscopy can give the radial velocity. And we have a lot of simulations and simulations of orbits also. And here it's just an HR diagram with some ages, like compared to the zero age mean sequence. So when you go to the older stars, older clusters, you always need to have deeper photometry to resolve the main sequence, because they are getting fainter. So the points are not very visible, but these are the globular clusters, the Milky Way. Also, some satellite galaxies are next. And so the Milky Way has 160 globular clusters, more or less. 1 order of magnitude more open clusters, and 40 globular clusters are in the bulge. So, which are these blue points here at more or less 8 kiloparsecs. And it's always hard to tell which ones are intrinsically in the bulge or are just passing by. We usually use the galactocentric radius or distance, less than 3 kiloparsecs, but we can also classify it dynamically from its orbits. But yeah, so these clusters are less studied than the others, obviously, because of the high reddening and about the crowding of the bulge. But we know that they are very old, around 13 billion years, and are enriched in alpha elements. So they had a rapid chemical evolution, chemical enrichment. So they were probably the first objects to form the Milky Way at redshift 2, or even before. Almost all the bulge globular clusters are formed in situ, as some recent dynamic analysis show. And we also frequently say if they are the building blocks of our galaxy, since they are the oldest objects we can observe here. So when it comes to metallicity distribution, if we look at extragalactic globular clusters, we have peaks in -1.6 and -0.5. And if we look for all the Milky Way globular clusters, this distribution is similar. So these peaks are similar. But if we look only to the bulge globular clusters, we see that the more metal poor peak is around -1, which is in this middle region here. And the more metal rich peak of the bulge globular clusters are around -0.4, like this gray line here, or the green, -0.4 and -0.5, as recently shown by VISCACHA 2024. So we see that the metal-rich peak is the same, more or less, but this that we call moderately metal-poor globular clusters are not the same peak, the global peak of the Milky Way. So during my master's in São Paulo, a colleague and we wrote a code for statistical isochrone fitting. It's called the SIRIUS code. This is the paper for reference. And it uses, you can use a lot of different models: Parsec, Dartmouth, Basti. It can include the membership of the stars in the fitting and derive these four common parameters in isochrone fitting. So the interesting part here is that it applies a Bayesian approach with Markov chain Monte Carlo, and the likelihood here it starts to get a bit complex because we have a two-dimensional plot to fit your model. So there are two chi-squares, one in magnitude, so the y-axis, one in color, which can be other filters, obviously. And to sum up for each star in the likelihood, we compare to the closest point of each star to the isochrone. So the isochrone is usually represented as a line, but it's a sequence of points or simulated stars with a fixed mass. So different masses, but same age. So this is how we compare the magnitudes and colors of each star. And as I said, we can include the membership, which I will tell you in a moment. We can include other terms here, such as the number of neighbor points in the CMG. So so that the giant stars can get more weight, higher weight in the likelihood. And maybe the most important here, the prior distributions, which you can apply in parameters that you have some information a priori. For example, the metallicity from spectroscopy, or the distances from variable stars, and so on. So the first application of the SIRIUS code was to multiple populations context. So my advisor, Professor Beatriz Barbui, was a member of this Hubble collaboration led by Gianpaolo Piotto. And we could use this data to fit isochrones and so on. And yeah, and I won't introduce too much on multiple populations because our last talk was about that. But basically, in these observations, they chose 3 Hubble filters that matches the bands or the lines in the spectra related to the CNO cycle. So you have some filters in the ultraviolet and blue, and for example, the central one shows the difference between first generation stars and second generation stars, where the second generation is enriched in nitrogen, for example. So here, using these filters, UV and blue filters, we could split the sequences of the CMD into 2 generations. and do an isochrone fitting, but not in DCMD because the models were not well calibrated. So we do a cross match of the stars going back to an optical CMD, and we see that the stars get mixed up here. And we derived an age difference between these multiple populations, which unfortunately was smaller than the uncertainties. So it's not a too strong conclusion. This is my paper from 2020. And after that, we kept fitting isochrones to globular clusters, bulge globular clusters. And we always get old ages for them, and especially for these clusters with metallicity around -1. So that I told you before, the moderately metal poor. So for example, HP1 of this paper of 2019, we had this 12.7 billion years on average. From 2023, NGC 6355, and so on. And the interesting part here, maybe the most important, is to plot the age and the metallicity derived for these clusters. Summaries of hope everything's fine. Yeah. So when you plot, and there are a lot of stars in this path here, and they are the globular clusters formed ex situ, so out of the Milky Way, probably, and were accreted from a dwarf galaxy or something like that. And the bulge globular clusters are up here, so they are very old also, but more metal rich. So, and the studies show that they were formed in situ, so they have a different chemical history of chemical enrichment. So this is also from this paper, which I am co-author. And, oh yeah, so another prior that I mentioned to you was the RR Lyrae stars. And here's a work that I did in 2022, which I used OGO data, OGO4, around clusters that we knew that were bulge clusters. So we did it for 6 or 7 clusters. I also added Gaia proper motions. There are some gray points in the background, which are the field proper motions. They're not that good. And so I could select these RR Lyrae that were indeed members of these clusters. And from the mean or the average of their mean magnitudes, and also with some new calibrations of Basti, zero-age horizontal branch models, and some proper reddening laws, we derived the distance with 5 to 8% precision. So this could be used as prior, or even better, the mean magnitude can be used as prior, so you don't. So iteratively in your fitting, you use the metallicity value that you are sampling and also the reddening value, and with this mean magnitude you can get the proper prior in the distance while you are fitting. And just, okay, 20 minutes. So the second part of this presentation, which is actually the main topic of my PhD thesis, is about the Magellanic Clouds. So clusters in the Magellanic Bridge. So also some details here about the LMC and SMC, which is a bit farther away. The SMC on average is more metal poor, but they are not the only constituents of the Magellanic system. We also have structures of neutral hydrogen, which are in red here. And they cover a huge extension in the sky. And they follow the Magellanic Clouds as as these galaxies orbit the Milky Way. So they are the Magellanic Stream, which is always behind the orbit, what is left behind, the leading arm, and the bridge in between these two. Also, and the bridge from these three structures is the only one that has a considerable stellar mass. So that's why we choose it to study the star clusters. So we have some recent simulations based on different epochs of HSC proper motions. They also have some different inputs. And there's a paradigm, let's say, about if the Magellanic Clouds are in the first orbit around the Milky Way, or if they are interacting for a longer time. So, and to study the stellar populations of the clouds and also from the bridge can give some important constraints for these models. So the bridge itself has a 20 kiloparsec extension. It has also some depth and some very few metallicity determinations based on quasars and background quasars and so on. Mostly it has a young stellar population with a lot of associations. And it was probably formed in a recent collision between the large and small Magellanic Clouds. So in this episode, gas and stars would have been pulled off from the SMC between 100 to 300 million years. And we also know that its stellar population can be divided in stars stripped from the SMC in the formation and stars formed in situ. So we have hundreds of clusters in the, actually more than 100 clusters and 300 associations in the, what we call wing. Is the start of the bridge, like with the SMC here. And these are the clusters that I studied. So, some water. For this, I used mostly data from the VISCACHA survey, which is a collaboration of Brazilian, Chilean, and Argentinian astronomers, which I'm part of. We use the SOAR 4-meter telescope, and to get the BVI photometry, deep CMDs, and the differential here, the important part is that we use adaptive optics. So here's a GIF with soil photometry without adaptive optics, and some which we can resolve much better than the stars. So we have photometry, actually the deepest photometry for 200 clusters, more or less. And we actually give preference for clusters in the outskirts, both of the SMC here in the bridge, but also in the LMC that would be here. So, because these outer parts would be more prone to dynamical interactions and so on. So I participated in the observations, the data reduction, and I'm currently the chair of the CMD working group of VISCACHA. Here it's very interesting. VISCACHA CMD for this old cluster of 4 billion years, Lindsay 113, and the age-metallicity photometry for the same cluster. So here I stopped in the completeness limit here, but we actually go 1 magnitude more or less shallower than age-metallicity, and as expected, larger photometric errors. But still, this is the best that we have with ground-based telescopes. And it's not doable to observe hundreds of clusters with age-metallicity. Here, a quick comparison with this mesh photometry, which has photometry for almost all the system, including the bridge, but it doesn't have adaptive optics. So the general CMDs look similar if you compare VISCACHA and mesh here, but when you go to the central regions, the adaptive optics is very pronounced, the effect of using adaptive optics. Okay. So I presented the SIRIUS code for isochron fitting. I also did a code for fitting king profiles to density profiles or brightness profiles. And so this is the king model from 1962. Here I also use Bayesian inference. It's much simpler than the isochrons because you only have 1 chi-square and you have an expression for the models and not a grid of isochrons. But here I derived the structural parameters and a new center for the cluster. So yeah, and actually there's something else, which is, so historically or traditionally, the density profiles are obtained from radius. Increasing radius around the center of the cluster, and you get some 10 points of density as a function of the radius. But to get more points, more statistics for this likelihood, we calculate the density around each star of the photometry. So with variable size of kernel and so on. But the final density profile is similar, but you have much more points, and you can also detect differences in 2 dimensions or derive parameters, and also get more points for the likelihood, which is what we wanted. So here, it's not published yet, this part. We have some things to test and to implement, some more complex models and so on. And another important part is the statistical decontamination. So because Gaia proper motions or Gaia photometry is not deep enough for this cluster. So it's good for these giant stars, probably, but we couldn't get decontaminate the CMD for such far clusters. So here we apply a statistical decontamination, which we get a central field of the cluster of the photometry. which is smaller than the tidal radius, and a field outside of this tidal radius. Actually, there are some grids here that are not very visible. And we compare the stars within these grids, and also we know the radius to the center, and we do some statistics on it to exclude some stars that are probably probably do not belong to the cluster. And we get a final CMD decontaminated like this. And for example, in this case, the isochron fitting could be confused for an older main sequence turn-off, for example, if the field is considered here. But we see that it's probably a cluster of 1 billion years. So, yeah. So here a comparison between VISCACHA and SMASH isochron fitting that I did. So the fact that we have more stars in the center is not very very important, like if you compare the parameters, but in other aspects of the data analysis, it can be more useful. So here I'm also working on it to study a larger sample with SMASH data, and so we can observe really the more important targets with VISCACHA. So some spatial distribution of the derived age of these bridge clusters. It was 33. We can see that we have more older clusters here close to the SMC, which is here, and more examples of young clusters in the middle of the bridge. Also here the metallicity, so we have the inverse thing, so more metal rich in the middle. We can plot the gradients of age and metallicity compared to the SMC, and we see that the older clusters in the bridge, so the clusters older than 300 million years, follow the age and metallicity gradients of the SMC, so because they were stripped from it, and the younger clusters do not follow, obviously, and they have a more or less constant metallicity around minus 0.4 or 0.5. And maybe the most interesting part, again, to plot the age-metallicity relation compared to chemical models. So the yellow points are my 30 clusters in the bridge, and we see that there are at least 2 dips of metallicity. So these bridge clusters are more metal poor than they should be according to the models. So this is a zoom in of this region, and these dips occur around 1.5 billion years and 200 million years. And it was probably due to an infall of metal poor gas, which then can accelerate the star formation. And at this epoch, we have the formation of the Magellanic String. So it possibly have changed something in the SMC that generated this dip. And also here it's more less clear than this other, but it's the this 200 million years the age of the bridge. So it's possible that during the formation of the bridge, you had some inflow of metal poor gas that So that some clusters are more metal poor than they should be. So at this point here, we didn't try to fit chemical evolutionary models to these points. But in the following paper from VISCACHA, which studied west halo clusters. So yeah, I didn't introduce the west halo, but it's another region in the outskirts of the SMC, on the opposite side of the bridge. And here they combine a lot of photometric data, and so they compared to the available chemical models, saw that there's this dip, and computed new models based on inflow of gas or collisions between the Magellanic Clouds and so on. And probably this will also be done to the bridge soon to discover what could have happened there. And another paper from VISCACHA after my thesis was with spectroscopic data in the Council triplet region to get the radial velocities and the metallicity. And this metallicity can be used as a prior. So it can be confusing, this figure, but I just want to show you that with this information and Gaia proper motions for giant stars, you get the vectors of where these clusters are moving and so on. So, and if you do the proper assumptions and include the potentials of the galaxies, you can get the orbits. And it's something that we also want to do. And I want to highlight two studies of other PhD students from VISCACHA. One is about the completeness, which adds some artificial stars in the field of view, and statistically, like they simulate artificial stars with different magnitudes and so on, but they do the completeness corrections based on the catalog, not on the image itself. So it's much faster, and the results are very similar to the traditional method, which is every time you reduce your image again, see if the artificial stars are detected or not. So this is a work from Gardin, which was submitted. Yeah, and probably this code will be available also. And the Siesta code, which is also for isochron fitting, and was also submitted and will be open source. It also has a Bayesian approach, but it doesn't use so it does synthetic CMDs with all these assumptions here, IMF, binary fraction, completeness errors, and use the Hertz diagrams with the densities to compare the observations and the synthetic CMD. So you can get the parameters that can best reproduce the distributions of stars in the CMD. And so here are some ideas that you can take home. So the instruments are developing fast, and also we need to get precise parameters for the clusters, possibly using priors. And it's fundamental to calibrate the models, and both the models from isochrons and also in the age-metallicity plot. The bulge globular clusters are strictly old, but they don't follow the age-metallicity relation of the ex-situ globular clusters. So here are what I just told you about the Magellanic Bridge. something that I didn't tell is that we did a new mass estimation for the bridge, stellar mass, and it's a factor of 10 higher than previously reported. So just based on these clusters that we analyzed, and also on the number of other clusters and stars, we got to the order of 10 to the 5, and it was 10 to the 4. And VISCACHA is disentangling the chemical history of the Magellanic Clouds, and we have these new tools to be released soon to be open source. And that's all. Thank you.
Well, and do we have any questions from here or on Zoom? And you can check the list. And so you mentioned several models, like the isochronous models that we use. What's the main difference in between them? I mean, are they special for special kind of population of stars or metallicities? Yeah, there was like 3.
Yeah, here, for example. So basically the differences are in the assumptions in stellar evolution. That's like the ingredients in the very beginning that they use. And the isochrones are slightly different. But for example, for parsec, for a long time, we didn't have alpha-enhanced isochrones. So that's why for the bulge, we always were applying Dartmouth and Basti. And yeah, things like that. So overshooting, some models can have, some, so parsec have. Also, binaries, this other rotation now is included in parsec models and are not in the others, I think.
So parsec is the most, let's say, complex, and then uses most.
Yeah, for the Magellanic Bridge, yes. But yeah, they are constantly developing.
So we have 2 questions here. Thomas?
So do these models take into account the effects of multiple star interactions in the clusters, or it's beyond?
The isochrone models or the
Isochrone.
interactions?
Because in regular clusters, there will be lots of interactions between binaries, exchange of partners, and that will lead to non-standard evolution as compared to stellar evolution and just binary evolution. So that may, I don't know if it influences undergones or not.
Yeah, I think they are included. Also, this rotation rotation variable that they are adding now are somewhat related to binaries, and like they include rotations of the cluster stars, and can, for example, explain extended main sequence turnoffs in CMDs, which were thought to be multiple populations. Or so yeah, these interactions of stars are also included.
So the questions you showed in these slides, they can show the likelihoods. So there is nothing about binary systems. So if there's stellar binary, we typically don't resolve it, and that would be above the isochrone, because in general we have to bias your estimate. The main parameter.
Yes, so not much for this case, but for the, yeah, here it's not too visible, but yes. So if you don't simulate the binary effect in synthetic CMDs, for examples, you neglect this, and you can get a fit more rather than it should be, or deviated. So,
Do you take that into account by the 18?
at this point, we try to exclude sequences that are not in this part of higher density. So these stars could be excluded. This SIRIUS code now includes the binaries, but not in these cases. But the last code that I showed to you, so siesta code, for example, this one includes the binary, both binary fraction and mass ratio. And then here it's also not too clear, but you get another main sequence here, and you can fix the binary fraction, for example, that better reproduces the observation.
Łukasz, you have a question?
Yes, thanks, Raphael. I just wanted to ask about the VISCACHA survey about the clusters. So it looks very nice and very nice comprehensive survey. I was just interested if there is any time domain component in that survey. So I mean, the same fields observed multiple times.
Yeah, so there is not yet, but we have already 8 years of observations, and we have already time allocated in solar for some years, and we are thinking about revisiting some clusters to get proper motions on. Not for variable stars, but for proper motions, relative proper motions. Probably.
Right, but you can also try looking in, because you are probably the deepest survey, so you can look for variable stars no one else can see, right?
Yes, that's right. Yeah, in 2 or 3 epochs.
Okay, thank you.
Yeah, I don't see any more questions. So thank you, Raphael.
Thank you.
But